Welcome to this explainer. Today, we're diving headfirst into what I can only describe as the ultimate cosmic true crime mystery. We're talking about a universe where entire massive worlds are just disappearing right before our eyes. And the wild part? We are finally figuring out who, or rather what, the culprit is. It sounds like pure science fiction, right? I mean, we map out these celebrated celestial bodies, carefully put them in our astronomical catalogs, and then, upon closer inspection, they're gone, just vanished without a trace. So how does a giant exoplanet pull off a cosmic magic trick like that? Well, the answer actually lies in the stars they orbit, and specifically their deeply violent and deceptive nature. Astronomer Ekaterina Island recently observed something that completely breaks the rules of what we thought we knew about planetary systems. She watched a system where a planet was getting absolutely hammered by intense stellar flares. But these weren't just random space weather events. They were purposefully aimed right at the planet, multiplying by a factor of 5 or 6 right when it passed by. As she put it, this is statistically almost impossible. And that bizarre anomaly sets up the exact mystery we're about to solve today. Okay, part 1, the case of vanishing planets. Let's take a look at our victims, the actual worlds that have seemingly been wiped from the cosmos. For years, Fomalhaut b was famous. It was celebrated as one of the very first exoplanets we directly imaged, literally written into the textbooks. And then there's Vulcan, officially called HD 26965b. This one famously orbited the real-life star of the fictional Star Trek planet. Trekkies everywhere were absolutely devastated when the truth came out. Both of these were massive milestones in astronomy, and both turned out to be complete illusions. When we pointed higher-resolution instruments at them, these planets literally vanished from our data. So who is our prime suspect? It's something called the stellar activity trap. This is a dual astrophysical phenomenon, where the roiling, turbulent magnetic fields of a star do two completely different, very sneaky things to mess with us. First, they actually mimic exoplanets, creating false positives that totally fool our telescopes. And second, they act as literal engines of destruction, physically destroying real planets that just happen to orbit a little too close. This trap operates in two very distinct ways. On one hand, you have the trickster, the observational illusion. Hot plages and cool star spots rotate across the star's surface, and because they're spinning, they distort the light in a rhythmic way that perfectly fakes the gravitational tug and transit shadows of a planet. It's a cosmic counterfeit. On the other hand, you have the brutal destroyer. Because stars aren't always quiet neighbors, they can violently erode atmospheres, swallow planets whole, and quite literally vaporize them. Which brings us to part 2, the stellar activity illusion. Let's uncover exactly how a star lies to our most advanced telescopes. Imagine the chaotic, boiling pot of stellar plasma as a massive orchestra playing completely out of tune, with different instruments messing up at different times. You've got asteroseismic P modes, basically trapped acoustic waves buzzing like a violin string, causing noise on a timescale of just minutes. Then stellar granulation, which is heat bubbling up like a booming drum, alters the light over hours. Active regions, like those starspots we mentioned, throw off our readings over days to weeks. And finally, entire global magnetic reversals that take years to play out. This overlapping, deafening cocktail of noise, that is exactly what creates those ghost planets in our data. All right, moving to part 3, engines of planetary destruction. But look, stars aren't just creating illusions. Sometimes the destruction is very, very real. And honestly, our universe is not a safe place. When stars like our sun age, they swell into massive red giants. If a planet happens to be in the way, it gets swallowed whole. It's assimilated, leaving behind a chemical signature of fresh lithium on the star's surface, which is exactly what we observed with the red giant BD plus 48 740. And what if a planet wanders too close to a supermassive black hole? The extreme gravity stretches it apart into long strings in a gruesome process graphically known as spaghettification. This whole thing culminates in a brilliant, devastating flare called a tidal disruption event. Now, if a planet actually manages to avoid being swallowed whole, it might face a slower, way more agonizing demise. A young planet typically starts out with a nice, thick, primordial atmosphere. But over millions of years, the host star aggressively bombards it with extreme UV and X-ray irradiation. By the hundreds of millions of years mark, this intense heat acts like a giant cosmic blowtorch, driving a process called photoevaporation. Imagine just boiling a pot of water on the stove until there's literally nothing left. Fast forward a few billion years, and all the gas has completely boiled away into space, leaving nothing but a bare, dead, rocky core.
This slow destruction creates what astronomers call the radius valley phenomenon. When we scan our galaxy, we find this weird, unexplained scarcity of planets that are 1.5 to 2 times Earth's size. Why this missing middle? Well, it's because these intermediate worlds just don't have enough core gravity to hold onto their thick atmospheres when that stellar radiation hits. They are literally transformed from puffy, gaseous sub-Neptunes into bare super-Earths. We're actually watching this happen right now to an exoplanet called GJ347b. It's evaporating so fast, researchers describe it as a slowly disappearing planet.
But wait, here is the ultimate, mind-bending plot twist. Remember that quote from the beginning of this explainer? In systems like HIP 7652, the exoplanets are actually triggering their own destruction. Through complex magnetic star-planet interactions, these close-in worlds act like a catalyst. They cause the star to unleash massive magnetic flares that are pointed right back at the planet. They're essentially pulling the trigger on the gun that's pointing directly at them. It's wild. Okay, let's look at part 4, AI as cosmic detectives. With all this illusion and destruction making exoplanet hunting so incredibly difficult, we need some serious forensic tools to fight back. First step in our arsenal is statistical modeling, specifically something called Gaussian processes. You can think of Gaussian processes as a mathematical lie detector. See, while a star spot comes and goes randomly, a true planetary orbit is a relentless, unchanging metronome. By treating stellar noise as a quasi-periodic random process, this math maps the chaotic, temporary noise of the star and completely separates it from the strict, coherent signal of a real planet. To take this to the next level, astronomers are turning to machine learning. Instead of just filtering activity over time, they use deep neural networks to look purely at the shape of the light, what's called the cross-correlation function, or CCF. Think of the CCF as the actual, unique fingerprint of the star's light. Researchers trained these networks on highly detailed daily observations of our own sun using the HARPS N solar telescope. By learning exactly how a star spot physically distorts the shape of that fingerprint, the AI can filter out the noise and isolate the true exoplanet signal hiding underneath. And the hard data from this approach is just incredibly impressive. When researchers applied these neural networks to real solar observations spanning 3 years, they successfully dropped the radial velocity scatter from 1.753 meters per second down to a remarkably clean 1.039 meters per second. To put that into perspective for you, 1 meter per second is basically human walking speed. That means we are detecting gravitational shifts in entire, massive stars at the speed of a casual stroll. That is an absolutely massive leap in our ability to pierce through the noise and see the quiet truth of a solar system. AI is also taking on the star's violent flares. Researchers used a random forest machine learning model to scan over 41,000 flares detected by the TESS satellite, wanting to know how many packed a destructive coronal mass ejection, or CME. The AI predicted that a staggering 47% of these events show characteristics of a CME. But here's the really surprising fact. They also found that the most energetic stellar flares are actually less likely to be associated with CMEs. It turns out the star's own massive magnetic field might act as a sort of cage, confining the very biggest explosions and stopping them from destroying everything in their path. Which brings us to our final section, finding true habitable worlds. Everything we've talked about today, understanding the intricate timescales of stellar boiling, recognizing the chemical signatures of engulfed planets, and deploying deep neural networks to correct our data, it all leads right here. By combining high-resolution spectrographs with these advanced machine learning models, we can finally stop being tricked by the stellar activity trap. We're stripping away the illusions, accounting for the destruction, and clearing the path to find genuine, Earth-mass planets sitting safely in the habitable zones of their host stars. But, this does leave us with a pretty startling realization about the catalogs of exoplanets we currently hold dear. We now know the mechanics of the trap. We have the AI to expose the lies. So as we turn these new, highly sensitive algorithms back onto our historical data, how many of our thousands of currently confirmed planets will turn out to be nothing more than magnetic ghosts, just waiting to vanish?